post on the outside post. If you think that I'm going too quickly or you want to know more information, I think the best thing to do is to just be forceful and make sure I turn around and recognize you and ask questions, and I'll answer the questions, and then that way we can adjust dynamically to whatever your needs are. I don't have a need to say certain things, I just have a need or desire to teach certain things, and so we have to do that work, that interaction. So just ask a lot of questions, that's what we're going to balance considerations. Okay, so what I began with last time, or what I ended with last time, is I broached the subject of proof-relevant equality. That's what I was talking about, the notion of proof-relevant equality. And I started to discuss this at the end last time. And the way I introduced it is I introduced it as a possible use of the notion of a family of types. The notion of a family of types could be a binary relation. In particular, I asked you to define EQ, parenthesis, I'll write EQ of nat, okay, which is supposed to be a binary relation in the sense that, in the proposition of type sense, that given two natural numbers, it gives you a type, which is to be thought of as the proposition that those two numbers are equal. And so the spec was, right, that this type should be inhabited. In fact, the way I defined it is the type EQ nat, pardon me, EQ nat, if I gave you two numerals, that in fact ended up, according to my definition, being definitionally equal to unit type, to be 1. And if you gave me two distinct numerals, then that ended up definitionally being the type 0, where M and N are different. So the spec is entirely a meta-theoretic concept in that I say, well, when given two numerals, this is what it's going to be. So another way of saying it is that the intuition is that EQ nat Mn, informally, it's supposed to mean that this is inhabited, because you see I chose it so that these would be inhabited or not inhabited. And using 0 and 1, I could have written that true and false if I wanted to. It's just a change of notation. And the idea would be, it almost looks like I'm defining a decision procedure to compute a Boolean, but here what I'm doing is computing a proposition, or computing a type, which to be thought of as a proposition, and that type is inhabited when, well, there's no good way to write this. Okay, I'll write M as N. I don't know what else to write. It's difficult to say. I could write an equal sign, but then what do I mean by that? So I told you the whole issue of equality gets complicated. It's going to get complicated in a moment, and I want you to see that. But the thing that I wanted to get to here was, one was the idea of defining a type, a family of types, by a piece of code that does a double induction. That's what I asked you to do on these two arguments. And it computes a type, so to speak, as a function of these two natural numbers. So that's, for many of you, will already be like a dizzying notion, depending on whether you've had experience with this type of thing before or not, which I don't know individually whether you do. So that was the first point. And the second point, I wanted to start thinking about this notion of equality, because the spec here sort of says I'm trying to define a notion of equality. And it's a notion of equality that's not like a Boolean test. And why is that? Because, well, we'll see. We want to scale up to other types besides nat. And at a certain point, it's no longer possible to specify it as some kind of Boolean test. And so instead, we wanted to compute a proposition. The same thing, it's an example of a concept that comes up a lot in programming languages, which these days are called contracts or assertions or whatever. They're computable tests that yield a Boolean or raise an exception or not. There's different ways to organize the details, but let's just say they compute a Boolean. And the problem with it is that they're not specs. I mean, they're just pieces of code that compute a Boolean. And so you can't say anything serious, right? You can't say some serious specification. So I think it's unfortunate that people learn like that an assertion is somehow a Boolean test. That's only a very low-grade degenerate case. So there's a similar thing that I'm trying to get at here, is I want this to compute a proposition. It's also true that for the natural numbers, I could define a piece of code that computed a Boolean, and then if I were to do that, then I could assign the type 1 or 0 according to the outcome of that Boolean test. So you could, that's a different way of defining EQ nat than the one I suggested to you, but that's perfectly valid as well. But that kind of point of view is not going to scale. So then I asked you a question, so because I wanted to launch into a series of further questions that are going to be provocative and are going to motivate what I will do. At least that's my plan. And so I asked you a question. So the question was, given an arbitrary, I don't know anything, let's think of it as a variable from n to n or nat to nat. Because I use m and n for terms, I better not call it n, let's call it n. Otherwise I'm going to get things that look strange. So given f and m and n, and well, I can write this in various ways. Is it the case that for, let's say, some mn and nat, that EQ nat, just to be emphatic, mn arrow implies EQ nat, what do I call it, f? Okay, fm and fn. So I ask you to consider that. So is it the case that, in other words, is this type inhabited? Is there something that you can write down that's in there? Okay, that was the question I posed. I hope that the talk here isn't there's not much I can do about that, I don't think. I know there's nothing can be done about the fact that it's warm here. Okay. All right. So the question is this type inhabited can be read as this implies that. So in other words, that is, do functions on that, that's just the particular case I have, respect this relation that you defined, EQ nat, or I defined, or we defined, EQ nat. And if so, you should be able to exhibit a proof term, and if not, you should have some argument why not. So that was the question I posed. I don't know whether I only got through typing it out on a message late last night, so maybe you haven't had time to think about it. Okay. So I will suggest that the answer here is yes. Okay. And what you have to do is you have to prove, so I can fix my m and n, that's sort of not so important, or I could just make them be variables. The thing to do is to strengthen the IH, so you can say, well, for example, if x or y are a nat, is it the case that for every f in n arrow n, and now the same thing that I just wrote, EQ nat xy, arrow EQ nat f of x and f of y. And my point is I want to strengthen the IH because I'll do this by a double induction, that is nested induction, double induction on x and y. And the reason that that's the suggested thing to do is because that's the way I defined EQ. I suggested to you to define it by, an iterated induction on m and n, or the arguments to it. So we'll do the sort of same thing here. And I'll just rough out the proof. You can write it out in type theory. But the point is I wanted the pi here because I want to strengthen the IH and make the statement about for all f's inside the induction. So the idea will be I have these cases. X is 0, which is y. And then I want to know, is this type inhabited? So I'll give you the inhabitant. It's lambda f, lambda, I don't know, z. And I will write here whatever your proof of reflexivity was. Refel of f of 0. I asked you as a lemma I asked you to find. I forgot to write that here. If you don't mind me squeezing it in, I asked you to define this such that for every x in nat, there's an inhabitant of x, EQ x and x. So that's what I mean by refel in this case. I asked you to define that. That's very easy to define by induction on the structure of the natural numbers. And I hope you did that. So the question is, why is this an inhabitant of this type? Well, the reason is that when these two things are zero, the way I define EQ nat is such that EQ nat 0, 0 is calculationally equivalent to 1. Okay, it's the way I define the function. You can just calculate that it's 1. It's not sort of a theorem that it's 1, it just computes to 1, this being AKA unit, AKA truth, whatever you would like to write that as. Okay, it's equal to 1. And if this is equal to 1, and then what I'm doing is I'm really just ignoring that. I don't even need to give it a name because that means the only possible element here is the null tuple. Okay, and then I just emit. I have to have a proof x and y are 0, so a proof that f of 0 is equal to, so to say, EQ to itself, and that's given by your lemma. Okay, so that's partly why I asked you to prove that lemma. And now if you look at the case, for example, x is 0 and y is a successor of something, well then you can, I'll first do the calculation. If you just look at the definition, EQ nat of, oops, I defined this thing, EQ nat, 0 and successor, in that order. I define that so that it's the type 0, which in this case is aka void or false, depending on which, spin around the triangle of Trinitarianism, and you can just write it any way that makes sense to you. So we can do it like that. So this is the empty type. Got a big hole in it, so it's empty. And then, so what does that mean? That means I need to produce something, lambda f, where I have a z whose type is 0, and then I need to produce something whose type is that. Well, that's just abort z. You see, because 0 error anything is inhabited by this function, lambda z abort z. Because it's a contradiction, you see, this is your contradiction. And the same thing happens here if you do x is successor of anything, and y is 0, then we should be able to, I have a slight hesitation because I have to look at my code. I hope this is true. If it's not true, I'm going to have to make it a little harder, but I want that to be 0, and then it's the same argument. And you can write the code in such a way that this is true. That's what I want to say. So this is a very, let me finish my line here. Okay. You can write the code in such a way that this is true. But what I will point out to you, which is a very annoying thing about dealing with this sort of type theory, is that the whole argument is sensitive to how you wrote the code. You can find crazy ways to write a particular program that is extensionally the same as some other crazy way to do it, but one of them will be better behaved with respect to these calculations than another. You're going to run into that all the time, okay? It's a very unpleasant thing because, so I should check, I'm pretty sure, if I wrote out the code properly, that there is a way to write that code, which I scratched out in my notes, so that this will come out to be true. If it doesn't, then this part of the argument is broken and we'll have to think of something else. But this was the idea. And now if you have the successor of two things, now I need to give them names. Y equals successor of y prime. Okay, so what we figured out is that, just for the sake of discussion, recall, you can calculate, I'm pretty sure this is true by calculation, that this is equal to, calculationally equal to the equality of x prime and y prime. You can read it as saying, these two things are equal if and only if these two things are equal. Okay, you can work that out. Okay, so that is, if you look at the way the code was written, that's the way it was defined. Okay, so now I need an inhabitant of this type. So first, let's write down what our inductive hypothesis tells us. And now you'll see why I had to strengthen it to do the proof. So the IH tells us that for every f in n or n, if you give me a proof that x prime, this is, now we're in the induction, so this is the x prime I'm talking about. If you give me a proof that x prime and y prime are equal, I'll give you a proof that f of x prime and f of y prime are equal. Okay, that's what the IH delta is. And what we have to show, let's just write it out carefully so you can see for every f and n arrow n, if EQ net xy, okay, arrow EQ net f of x and f of y. I'm just being ultra, careful about writing it out. Because computers are like that. You're going to have to learn to be this careful because you have to be quite precise when you're doing a proof for a computer. So we can do that. So let's just say, so what do? Is we suppose we have such an f, and we suppose we have such a proof, I don't know, I'll call it P, xy, okay, and then I have to show, right, that I have something in EQ net, fx, fy, okay. So remember that the case we're in is the x and the y are, I wrote equal sign here, that was an informal, because I'm writing an informal argument. The way it will work out is what will be plugged in there when I wrote x, it'll really be successor of x prime and successor of y prime. So this will end up being equivalent to x prime, y prime, because x and y are the successors. So the Blackboard convention, if I wrote those, what x and y are using some other notion of equality, it all gets confusing. But in reality, what happens is it plugs in successor of x prime and successor of y prime. So that's what you would see here. And then by examining the code again, you have to look at the code you wrote. And for EQ, you should get that to be definitionally equal. So now we have that, okay? So now how are we going to use the inductive hypothesis? Well, the whole trick is this, is we take f in the IH to be f composed with a successor. I take this f, which is universally quantified, plug in f composed with a successor, use P, okay, so if we call it the IH, let's take an IH, so I take IH, I apply it to f composed with a successor, and I apply that to P, which is my proof that x prime is equal to y prime, and what do I get back? I get a proof that EQ of net f composed with successor of x prime and f composed with successor of y prime. And now, if you just calculate again, well, we have to see what the definition of composition is. Okay, it all gets rather, tedious in a way. That works out to be f of x, because x is successor of x prime, and that works out to be f of y, and that's what we wanted to show. Okay, so that's the kind of argument. Yes?
Yeah, sorry, could you restate for me where the P comes from? So is it just something that's...
Because I'm trying to show this, so I let f be where did it go here? Let f be arbitrary, and now I'm trying to show an implication, so I assume the antecedent, which is this. And then the case I'm in is x is really successor of x prime, and y is really successor of y prime. I'm continuing from this case. Okay, and this type is the same as that type if you define DQ of net in the right way. Okay, and unfortunately, I just want to emphasize it's very sensitive to how you write the code. Okay, that's and it'll turn out. I'll show you a little bit later. And of course, from your own experience, there's a million ways to write a given piece of code that satisfies a certain spec, an extensional spec. Okay, so what I'm really trying to get you toward is the notion of extensional equality. We'll get to that later. Okay, all right. So that's where the P comes from. It's an assumption. Okay, and now I have to exhibit an element of this thing, and that element is going to be IH applied to this, applied to that. So what's nice, if you don't have experience with type theory, what I hope will be appealing to you, which was electrifying to me 35 years ago when I first came across the subject, is you're just writing code. Really rather nice, okay? And the idea that these seemingly disparate ideas, like especially if you go back in time like that far back in time, it was the Wild West. I mean, nobody had ever shown me anything remotely like that. You know, it was very, very advanced at that time. Nowadays, probably 3/4 or more of you already know all this kind of thing. But if you don't, I hope you'll take the moment to have the pleasure of understanding that the proof, writing a proof and writing a piece of code are very similar to one another. That's what I do. Okay, so that's the beauty of this kind of intuitionistic framework that we're developing. And of course, you know, I'm showing one slice of that world, and there's lots of other things too. Frank has been showing you things, Ed has been showing you from a categorical point of view. And what's remarkable is the confluence. You know, I felt 35 years ago, without really great substantiation, it's one of those things that people are inspired by. I felt the conviction that this is absolutely the right way to do things. There's no question about it. You know, and I devoted my career to it. Now, could I have proved to you that that was the case at that time? Of course not. But you know, this is how things get done. You know? So I thought, this is too beautiful. This cannot be ignored. This has to be the right way to do things. So Constable was showing me arguments like this, and I was just like, whoa. Great experience. So, okay, so that's the kind of thing that I had in mind. Okay, so that's the first step. Now there's something weird or something very special, yes, Carl, something very special going on here that's I'm going to call into question in my next board.
I missed the strengthening to the inductive hypothesis.
Oh, I don't fix the F in advance. The way it's stated, I stated it as fix some F in advance. And now, can you tell me, does this imply that? Well, the way I prove it is I prove that every F has that property, then whichever one you fix in advance, I'll pick that at the end. Okay? And I need that because on the recursive call, I call it with F composed with successor. The F isn't staying fixed as I go along. I choose a different F. On the recursive call, I give it a different F.
But what I'm not seeing is why doesn't the inductive hypothesis just directly imply what you're, as it's written there? Why doesn't it?
Well, I would consider this to be directly implies, but maybe what more do you?
Well, it says for all F
Well,
equal to F.
yeah, so it directly applies it in the sense, exactly the sense that I choose F to be F composed with the successor. Did Clement answer your question?
It doesn't say for all X and for all Y.
Yeah.
Oh, did I forget all X? Oh, yeah, I missed that out, didn't I? Yes,
Yeah, it shouldn't have.
yes, this should go, that's for every X and every Y. Well, no, I have, that's what I have here. And I'm doing the argument by induction of every Y.
I was just saying that we have suck of X prime and suck of Y prime, and that's why you don't just like really.
This X prime and Y prime come from the fact that I'm in the inductive stuff.
Yeah, that's it.
Okay. Yeah. I mean, it is immediate in a way, but I sort of wanted to show the gears turning. Okay. So that's first question. So now the next thing that comes up is, so I picked this EQ and NAT or NAT, and it looks as though it's behaving like equality. So at least the functions are respecting it, so that's a good thing. Okay. And the spec tells you that it should have the meaning of equality. But now what happens to you? Suppose I now start saying, well, okay, NATs are fine and interesting and well and good, but there are other types in the world. So what do I do? So if I'm going to continue in this way, what I have to start doing now is defining what EQ of 1 is. Okay? And I'm going to define that to be lambda x, lambda y, 1. Any two things in 1 are equal. Okay? I have to define what EQ of 0 is. That would be lambda x, lambda y, 1. Any two things in the empty type are equal because there aren't any. I was tempted to write 0 there. Okay? Just to be simple, let me write what is EQ of A cross B. Well, it should be this relation, which is a little trick of the light here, a little notation that's convenient. It basically means they're equal in, the first components are equal in A, and the second components are equal in B. So I could write that out if I want. So that'll be lambda x, lambda y. It's a little tedious, but let me just do it so you know what I mean. first of x is first of y, and EQ of A, or EQ of B, excuse me, second of x, second of y. Okay. I won't start writing out every single definition because I have a larger point to make, but I can, in a sense that you can define what that must mean, okay, and agree with me that that's a sensible notion, okay? Let's figure that out, okay, so we can put that as an exercise. Okay, and now I can go further, but here's the one I want to get to straight away. Before we even get to dependency, it turns out that dependency doesn't change my point very much, so I'll just look at these types for now. And I'm going to define this to be EQ of A, arrow, no, I think I need, no, the arrow will be fine. In the dependent case, I have to be a little bit here. Okay, EQ of A, arrow, EQ of B. And let me say what that's going to be. Well, I'm defining it to be, what does it mean for two functions to be equal? Okay, in the type A or B. So here are my two functions, undapped to lambda G. And now I want to say they take equal arguments to equal results. Okay, so it's going to be the type for every x and y in A, such that they're equal. I want to know that this is equal. Like that.
A should be a G.
Now, I'll mention to you that it's very common to get confused in situations of where you need a lambda and where you're going to need a pi. Right? And some languages have notation that encourages that confusion. Okay, and I'll just call it out to you. You're bound to have the occasion, I'm sure, when you are get confused about whether I should write a lambda or write a pi. So this is a lambda here, and this is a pi. A pi is not a lambda is not a pi. There are languages that deliberately confuse those two things for reasons I won't go into. Okay, but I just want to emphasize the quantifier structure. Because what I'm trying to do, right, is I'm taking in two things of the indicated type, and I'm emitting a type.
Before we get to those subtle distinctions, doesn't
did I
that
make a
supposed to
mistake?
mention G?
It wouldn't be, sorry, who's speaking?
Me?
Oh, you are.
Isn't that supposed to mention G?
Somebody, it's supposed to mention G somewhere, yeah, sorry. Obviously, so you can write it like that. Okay, so I could now do sigma and pi. You can do those yourself, how about? Okay, so you can do sigma x, and it's not significantly different from what I already have. So I'll leave those as an exercise because this is a generalization of that, and this is a generalization of that, or vice versa. These are specializations of those two. Okay, so I won't mention what those are. It's not important for me right now. So now I ask you the question. There are various ways to ask this question. So the question is, can I show for A and U and X, Y, and A, X and A. If this is supposed to be a notion of equality, which is why I spelled it EQ, I'm leading you down the garden path. Okay, but I spelled it EQ. So you would expect that it is reflexive. So let's do ruffle AX. So the question is, does that exist? In the case that A is nat, I asked you to do that for okay? Right? All right. And what did we just finish proving? The case for A is nat arrow nat. If you plug in nat arrow nat and you spell out what equality, well, this should have said equality at A, okay? Then you would see that that's the question I raised before, okay? Because it would say, given two EQ things in nat, is the application, well, yes, for reflexivity, so the reflexivity would be F and F. And I'm asking in the previous four, is F of X equal to F of X, or F of Y in nat, okay? So I just got through proving that to you, so that looks good, all right? So then you leap to the conclusion, no doubt, that, yeah, probably that's true, right? That's a problem. Okay? This is one of the central problems of this sort of type theory that is not a problem in the neutral type theory. Okay? So you'll find that out. Okay? It's a nasty problem because functions in type theory, as I've defined it so far, aren't functions. Okay? They're, I don't know what to call them. Okay? They're some kind of transformation. Okay? And here's what I mean. Consider the type A, I'll define that to be nat arrow nat, higher function. Okay? So what is it that I want to show? For that particular choice, the question is about all A's, but I'm going to hit you with a particular A. Okay? So what I need to show is that for F in type nat arrow nat, for F in this type, okay, I want to show that EQ at that type, if you don't mind me putting ditto marks there, that's the turnstile. I want to show that this is inhabitable. In other words, it's the REFL object, but I want to compute what that REFL thing would be. Okay? So that's what we want to do. So I don't need ditto, I'll write A because that's what A is. So F is an A is defined like that. Okay, so let's expand what that means. A is defined to be this type, okay? So what this means is I need to find something which is in this fancy thing. For every X, Y, well, I'll call it F and G. So let me call that capital F because it'll have my notation. So let me call that guy capital F. Things will look nicer if I do that. So what it's saying is for every F and G and N arrow N, if F and G are equal as, net arrow net, if they're equal as elements of net arrow net, I want to say that the application of capital F to F and capital F to G are equal as nets. So I'm trying to, I expanded this. I want to show this, okay? By definition, on the left-hand part of this board, this turns into that, okay? Which turns into something even more hairy. So what I need to show is, what does this mean, okay? Right, well, let's just stop right here before we get it. So I want to say, if you give me F and G, oh, there was an arrow missing. This should have said arrow EQ not. I knew something didn't look right. For every F and G, EQ FG implies EQ F of F, F of G. I had to wrap, okay? Is that clear what I wrote? No? Okay. So the question is how, so now what I would ask you is, we can further expand because this is a big quantified formula that says something about for every X, Y, EQ nat, okay, X, Y, arrow, EQ nat, okay, FX, GX, X, Y, GY, okay, that's what that actually means. I'm sorry, that's what this thing actually means, pardon me. So this thing actually means some quantified formula, okay. So the first thing I will observe about this, just to, maybe this may or may not be helpful to you, as I go up the type hierarchy, the quantifier complexity of the formula gets bigger and bigger and bigger and bigger and bigger, okay? Gets more and more and more involved, okay? So if I were to expand this in place and write it all out to you, you might be able, and then you might be able to keep that in your head, but if I went one more iteration, you absolutely would not be able to keep it in your head, it's too complicated. Okay, but in fact, if you just let it, work it out like I've done, you can keep your wits about it. So the question is, should this be inhabited? That's what I'm trying to show. I asked you to consider a special case of reflexivity, and the statement would be, works out to be this. Okay, this basically, is that type inhabited? Well, let's think about how I would go about proving it, okay? So I do need to know what this means in order to think about this. So what I have is, I have my F and G, And I have this assumption, which is a little bit complicated, but it's of the form for every x, y, nat. I'm just going to spell it out larger so you can see what I wrote there. Nat x, y, arrow, EQ, nat, fx, and gy. Right? Yes. Okay. And then I want to show something in, this is what I want to do here. I wrote it out again because I wanted to emphasize something to you. So you're trying to prove this formula. So you kind of keep in mind the principles of cut elimination, which I haven't proved to you and stuff, so there's lots of, I'm going to do some things that I'm going to claim are necessary that you really have to argue are necessary, but let's just say, what am I going to do? Take f and g to be general functions from n to n that satisfy this property, and now I want to come up with a proof that these two things compute the same number. Well, if you try to find an inhabitant here, if you try to find this guy, I would ask you, what exactly are you going to do? Because this is a variable, that's a variable, these are variables. So I can't computationally simplify. I have a definition for EQ and NAP, but nothing applies. These are just variables. F applied to F. It's a variable applied to a variable. That's a variable applied to a variable. So in terms of calculation, you get nowhere. There's nothing to calculate. Okay? And the same applies up here. I can't calculate that down in any way. I can't calculate that down in any way. So, I don't have any options so far of doing anything with the EQs, like simplifying them. That's not available. Okay, so if I can't do that, then the only thing I can think of doing is I let f and g be arbitrary, let h be a proof of this fact, and now what? Okay? How can I use this hypothesis? I have to come up with two numbers and a proof that they're equal, and then use that fact for those particular numbers to get where I'm going. Well, the truth of the matter is you're not going to be able to do this. Okay? So this cannot be filled in. In the type theory I've given you so far, DTT so far. Now, we'll talk about other things shortly, but so in keeping with my synthetic style here, I'm synthesizing type theory, so I've gotten a certain way, okay? So I want to keep that in mind, okay? So it cannot be written in DTT so far. What does that mean? Well, that functions in this type theory are not extensional. Because here's a functional f, capital F. Giving equal arguments, there doesn't seem to be any way to show, and one can construct a model and show that it's false, okay, in that model. There's no way to prove, okay, that f of f and f of g are the same. And I'll give you some interesting example of where this can go wrong in a minute. So what it means is that the function type, in general, a arrow b, is not a type of function. Functions like you learned in math. Functions in extension, one could say, to emphasize it. It's not a type of function. It's called that, A arrow b. I mentioned this to you before. Watch out, right? People are selling you goods, right? Be careful, okay? So it's called A arrow b. It's called the function type, or the exponential. But it doesn't have the key property that you'd expect it to have, which is it takes equal things to equal results. You're not able to prove it. Now, what will turn out to be the case is it's consistent to assume it, okay? And I'll discuss that. But it is not provable in the formal type theory. This goes back to what I said to you in a previous lecture. We're looking at a formalism that has a bunch of rules. There's always going to be stuff missing. So there's a game to be played. Amongst the things that are missing, which things do you bung in? What do you take as axioms and how do you justify them? Complicated and not very easy to answer. It's the nature of formal systems. And it's why, from a foundational point of view, I find them very unsatisfactory. But as analytic tools, they can be useful as analytic tools, and that's the way I view it. Okay? It can be used as an analytic tool. Okay, so what does one do about this? Well, so we have a problem that the things called functions aren't behaving like functions. So what can we do? Well, what you can do is One move which has been made and been used heavily over the last 20 years and is widely reputed to be hellish, and you'll see why, is I can define the following thing. What I can say is I can define L of A to be, by definition, its type is going to be A arrow U, and I'm going to define it to be lambda x EQAXX. So I'm going to say the true or valid elements of type A are the ones for which reflexivity holds. Okay? So that's the idea. And now I can show you it is in fact true. So I can define alpha A. Now I can actually prove, now you can prove this general reflexivity, but in under a stronger assumption. Well, here it then becomes trivial to prove reflexivity, because if I say I can actually prove easily for every x in A, if it's a genuine and not a bogus element of type A, then, of course, for every, I can say it's equal to itself, because that's by definition. So this is characterizing you can use various words, valid, or reasonable, or well-behaved, or I don't know, whatever words you want, okay? The correct word really is extensional. If you give me an extensional element of that type, one for which reflexivity holds, well then reflexivity holds, so that's quite trivial. Well, we'll consider those to be the legitimate elements of that type. And now I can define a notation. And the notation is M is epsilon A, if and only if there's a proof that L A of M holds. This means M is truly, extensionally, an element of type A. This is a behavioral condition. Right? This is telling me that M behaves according to the specification capital A. All right? That's what's being said here. All right? And then I can define M equals N in A with the epsilon, and I'll define that to mean there's a proof that EQ of A, okay, I should have, if I wanted to get my notation consistent, I'd capitalize that. So EQ of A, M and N. And this is defined where we presuppose, that's the usual way to do it, is you presuppose that M is in A and N is in A. So M and N are legitimate elements of A. This tells us that they are equal as legitimate elements of A. Okay? And you carry out your type theory in this manner. Okay? So this notion is called realizability, or type refinement, or, well, the old-fashioned term is something called HEO, the hereditarily extensional operators. Let's not worry about that. It's a classic proof theoretic classification of functionals called HEO. Okay? So what we're looking at is HEO. Yes?
Could you give a small example of an A that is not extensional?
It's not the A, it's the M.
Or the M?
Yeah. Yes, I will do one for you. Okay? Now that you ask, I'll do it. Okay, okay, so here's how I'm going to do it. I told you things are getting complicated, so I'm trying to be very, very careful. So I hope I don't screw up seriously. All right. Okay, yes, I will do that. But give me one moment, and I will explain that in a moment. So what is confusing you and what is behind that question is, every definable function in the syntax I gave you has the property that it's going to be extensional. That's the sort of thing that is informing your, if I write down any particular lambda, it's going to be a sort of a well-behaved thing. So the question is, what do we do? Okay, what do we do? So there's something called the fundamental theorem. Let's not worry about this, okay? So the issue is about the unknowns, about the variables, okay? Because the variables are to be thought of as yes, anything you can write down in theory can be plugged into that variable. But the variable is to be thought of as ranging over things in various kinds of models. Okay? So for example, I'll give you an example from total down-to-earth hacking experience. When you have, it's the idea of foreign functions. Okay? In a programming language, you have foreign functions. So when you write f as whatever the notation is, but when you write the equivalent of f as nat arrow nat, it could be some assembly code. Okay? You don't care. Okay? Provided your language is set up to treat it extensionally, then all that matters is its I/O behavior. It obeys the call and return sequence. So you don't care that it's a foreign function. So type theory is designed to be open-ended in the sense that you don't care what the functions really are. You care only about how they behave. All right? So that's the idea that is behind what I'm going to say. Okay, so let's look at an example. All right. Okay, so let me gather my thoughts. I hope I don't have to backtrack anything. So the example I want to look at is the following sort of empirical fact. Empirical fact is something called Church's law. Right? Church's law is maybe the only scientific law in computer science. That's the only one I know about. Okay, which says that any programming language you can ever write down amounts to the same thing, at least with respect to computation on the natural numbers, amounts to the same thing as a Turing machine or a lambda calculus or whatever. Okay? That's Church's law. It has the character of a scientific law. It says you carry out any experiment, invent your programming language. It will turn out that, okay, it's going to be the same, define the same number of functions on numbers as lambda calculus. Okay? So it has predictive character, and it has empirical justification. Okay? So it's a scientific law. I would wish for you to call it that. And I'm trying to change the world here. Okay? It's always called Church's thesis for some reason, but why? I mean, it's a law. In fact, it's the only law. Yes?
Does that law apply to quantum programming systems as well?
I can't hear it all.
Does that law apply to quantum?
Quantum programming system?
Well, it could be, but let's say the criterion that is used for the law is about functions on the natural numbers. I don't know of any result that says you can compute more functions on the natural numbers.
Quantum systems can be simulated by classical systems
Maybe.
in exponential time or something.
I didn't hear what that was.
Quantum systems can be simulated by classical systems.
Well, that's
in
also
exponential
true, yeah.
time.
So these arguments are always simulation arguments, so that's the right remark to make. I should have answered that.
So, on the first day, you made a point about strictures, not affordances. Don't commit to too much up front so that you can add things in later. That was sort of the principle.
I didn't get, I'm sorry, can you speak louder? I'm sorry.
Sure. So at the beginning of the class, you made a point about not committing to many principles at the beginning in order to have the option to accept them or reject them.
Right, exactly, yes, right.
So
The non-extensionality here could be considered, from your point of view, that's what I'm about to make.
right, yeah. So I'm wondering why. I don't really believe you should do this, but why not start without extensionality so that in the future maybe you could add Church's law as a principle inside your programming language, or not?
That, what, sorry?
So that
Why not add them?
in the future you would have the option to have Church's law as a feature in your programming language.
Oh, that's what I'm about to talk about, yeah.
Okay.
You're a step ahead of me, so that's where I'm headed, thanks. Okay, so I'll do that. It leads to two very different ideas of mathematics, of constructive mathematics. What I want to do is distinguish constructive mathematics from recursive mathematics. Okay, and they're very different things. Okay, all right. So let's do this. So, by the way, this move is also known. I forgot to say it. It's also known as senoids. Okay, where the idea is that you forget about m:(a) anymore, and you only work with epsilon. And every type comes equipped with EQ that you define with it, and then you have to manually show that everything is well defined. Because to show that something is in EQ of A or B, you've got to show that as a function, it's well defined with respect to the specified equality on A, in the sense of giving you the equal results in the specified sense of equality on B. And that whole laborious process is called senoid hell. Okay? It's a terrible, terrible way to live. Okay? So that has been, as a practical matter, completely unsuccessful. Okay, let's talk about extensionality in Church's law. So Church's law is an empirical fact about any kind of programming notation that, to my awareness, has never been refuted. If it were to be refuted, then some other law will have to take over, I assume. Okay. So within its range of validity, it's never been refuted. Okay, so that's the way it is. Okay, so Church's law, so what Church's law is okay, so here's what I can do. I can, if I wish, try to internalize the empirical fact of the validity of Church's law as an axiom. Okay? Because there's a question of what do you build into your type theory and what you don't. When you're working with a formal type theory, where it's all just a bunch of deductive definition, I can do whatever the hell I like. So I want to show you, like, well, there are more or less good ideas or bad ideas. So here's one. Okay? So you sort of feel like you want to import everything that's true. Well, I don't know what your theory of truth is. One would have to develop a theory of truth. But certainly in the sense of a scientific law, it's true that every computable function on the natural numbers can be given by a Turing machine, let's say. So this can be internalized as an axiom. I'll call it CL. And what it says is, for every f in n arrow n, there exists an E in n, which is the Gödel number, okay, of a Turing machine. That's the way that you're supposed to read that. Okay, I'm writing n, I mean that, but I'll write n, okay? N arrow n, such that, what? Well, I can write it like this. EQ, nat arrow nat, f, and the standard notation is curly brace of E. The function into the interpreter of E, that's interpret E. So that's interp E. Treat E is the Gödel number of a, well, whatever, a lambda term, a Turing machine, whatever you like, and interpret it as a function that takes numbers as inputs and produces numbers as outputs. So that's curly E. Okay. So this is a statement of Church's law. Okay. If you want to expand this out, this just says, this part can be rephrased as, for every x in n, because of the nature of the reflexivity of the natural numbers and the nature of the natural numbers as planetary objects, I can write this equivalently as, for every x in nat, I still have to have EQ of nat so far, because I have no other way of talking about equality, f of x and curly E on f. Okay. That's a textbook looking thing. Okay, that's what I mean by that. Okay, so that would be Church's law. Now, there's a fact that you can prove, I want you to prove for yourself. In dependent type theory, every total relation contains a function. For every x in A and for every y in B, if I have, excuse me, there exists a y in B, there is given a y in B, which is Rxy. That says R is total. For every x in A, I can exhibit a y that relates to x. Okay? If that's the case, then there exists a function f which goes from A to B such that for every x in A, it exhibits for you the witness to the fact that x is related to something, namely f of x. You can just write down a proof of that in 30 seconds. Okay, you should be able to do that. I refrain from using certain terminology. I'll just say that this is what it is. Here's a way to think about it. Because of the strength of constructive existence, the hypothesis contains within it, the only possible proof of such a hypothesis is one that contains within it this function f. So I can just pull it out. Okay, so prove this as a homework. Okay, that's very easy. So let's apply it here. So a consequence of Church's law is that I have an inhabitant, there exists an f whose type is n arrow n arrow n. Oh, the method to my madness starts to reveal itself. Funny I chose that type before. Okay. Such that, well, I wrote exists sigma. Let's write it as sigma. Such that for all f of n arrow n, what do I want to write? I want to write that E cubed nat arrow nat. Just to be brief, I'll write it like that. F of F, F, and F of F interpreted. So what is that saying? There's a decompiler, okay, that takes in a function f, so-called, an element of type n arrow n, and computes a Gödel number of a Turing machine that behaves, has the same I/O behavior as f. So this is extensional equality. It says they have the same graph, right? It says this and this function have the same graph, they have the same I/O behavior. Yes? So the step from here to here is an application of that fact. Yes, do you see that? Okay? Because I have, for every n arrow n, there exists an n. So I'll pull out this function that, given an n arrow n, chooses the n. Okay, so it should have said sigma. Right, like that. Okay. Then it chooses that n, and then it has the property that for everything you give it, it tells you that EQ nat arrow nat, f is related by EQ nat arrow nat to that particular function. So this chooses the Gödel number. This is a decompiler. That's what's happening there. So now, what do we want to say about that? Well, there are several things I can say about this. One is that should be, okay, so it interacts with this principle of extensionality. So here's the thing I want to say with you, okay? You can now do one of two things. You can either say functions are extensional, in which case you cannot have Church's law. I'll explain why in a minute. Or you can say functions are not intentional, extensional. And then you, if you want, you can have Church's law. This leads to, this view is what I would call constructive mathematics, or intuitionistic constructive mathematics. This view is what is called recursive mathematics. And this is more characteristic of what is frequently referred to as the Russian school of constructive mathematics that was pioneered by Kolmogorov and Markov and others. Okay? Is in this style. Constructive mathematics, as it's currently conceived, is in that style. The functions should be functions, but then you can't have Church's law. Well, why? If all the functions were extensional, so what would that mean? It basically means I'd switch all these to epsilons, right? That would be the notation I would use, okay? Because that's the notation I broached over here. I'd have to work that all out with you, but you can see what I'm going to mean here. Treat them as epsilons, okay? This has to be a valid number. It has to be an extensional function. This has to be a valid member of that type. It has to be extensional. It carries end to end, okay? That's what I would switch. So if you want to work extensionally and do what I think most people these days mean by constructive mathematics, you can't have Church's law. Why? Because it implies, in particular, that n arrow n in extension is countable. And you can refute the countability of n arrow n if it's thought of as functions in extension. Another way of saying it is, it implies that equality of functions in extension on nat arrow nat is decidable. Why? Just decompile them both and see if you get the same thing. And why must that be the right answer? Because capital F is extensional. The decompiler must respect equality in its domain. Okay? So two consequences are the function space n arrow n is countable, you can refute that. Function space in extension is countable, you can refute that. Equality of functions in extension is decidable, you can refute that, if you have extensionality. So you can't have Church's law. So from that point of view, Church's law is a blasphemy. It sort of says, I know God's programming language. I know that every function that God has created from end to end is actually written in Turing machine code. Okay? So it's blasphemy. Okay, you are presuming to know the mind of God. Okay, yes.
Can you have a propositionally contracted version of church's law?
Pardon?
Can you have a propositionally contracted version of church's law and have it still be consistent?
There are many subtleties, so let's, I'm not going to answer that. We can take that offline, let's say. Okay? Because it will then broach things I'm not ready to broach. So, yes.
That's what I was-
Same question, yeah. There are many, many subtleties, but I'm well aware where I'm stepping on stones from one to another, and I'm hoping not to fall into the water. Okay, so that's the thing I would like to get across. On the other hand, if you don't do this, if you don't want to insist on extensionality, if you want to allow that things are intentional, then F:(n) is not necessarily identified up to extensional equality or capital F and so on. And then it's consistent to add Church's law to the type theory, so that you know that every function is given by a Turing machine, and then you can argue on the basis of knowing the code, knowing what the code is. That's not math, if you're asking me. Okay? And indeed, this is inconsistent with classical mathematics. That is, you can get results that are just contradictory to things you learned in school. Okay? Good or bad, I don't care. You can have your opinion, okay? But it's a fact. This constructivity is consistent with classical mathematics. That, I think, is an amazingly great thing, because, as I will show, I hope, by the time I finish my lectures, the type theory, when done this way, is compatible with adding in other axioms like the law of excluded middle in a controlled way, and that will lead to a perfectly well-behaved system that replicates every result of classical mathematics. Everything in classical math, when doing, I'll use the word constructive for this choice panel, everything you do in classical math can be understood constructively in this setting. Okay? That's a really great thing, because that means when I want to do things constructively, I'm not in the position of having to say, I'm sorry, half of what you know is wrong. Okay? Forget it. All that stuff, all those proofs you thought were proofs, those aren't proofs. Okay? That's what I would have to do if I adopted this point of view. I would be in the position of trying to tell you that everything you know is wrong, or half of what you know is wrong. And you're not very likely to go along with it. Now, you can say recursive mathematics is an interesting thing in its own right, it's fine, and I don't have anything against it, or whatever, it's nothing like that. But it's a different enterprise from this enterprise. This enterprise is, let's enrich the expressive power of our language, of our mathematics, by making distinctions that are not customarily made, so that I can reintroduce them in a controlled manner and recover the traditional methods. But I can also expose ideas that are not exposed if you take those additional assumptions as a given. So to me, this is a much more beautiful and useful way to proceed. And this is, for me, my personal opinion, an isolated branch of recursion theory. Okay? I mean, that's just a personal opinion. I don't mean to impose it on you, but they're different enterprises. That's all I'm saying. They're just different enterprises. Okay? So there's your example. Okay? So this decompiler cannot be extension. Okay? So that would be an example. Okay, so now let me move on from there. That's already an awful lot to digest, but I think it was worth my while and your while to carefully go through that so that you can understand more fully what you're doing, okay, what's going on with type theory. So this begins to get in, so now we're into this issue of equality, okay? So now I want to resume that discussion. I mean, it's all about it, but I want to continue that discussion another way. Okay. So when you look, when Constable talks about New Pearl, I don't know what notation he'll use, but the New Pearl system doesn't use those notational conventions. It uses some other ones, but let's not worry about that for right now. We'll leave that for Bickford and Constable to sort out. But conceptually, this is essentially what is going on. It's actually slightly more subtle than that, but it's the essence of what is going on. And if you work this way, because functions behave extensionally, and for other reasons which I'm not explaining here, everything goes very, very smoothly. You never have to niggle about with, did I write the code for that thing exactly the right way to get this proof to go through, or do I have to suffer? Okay, I never have to worry about carrying along notions of equality and manually verifying that everything is well defined. Okay, that's a humongous, horrible thing. It's, in principle doable, but you don't want to do it. Okay? So the advantages of NUPRO in that respect are huge. Okay? And so, all right. So now what I want to do is discuss another direction, okay, that has recently been exploited that also achieves a reconciliation with traditional mathematical principles, but also expands them in ways that have been quite surprising. So all of these topics that I've mentioned so far, I will come back to, okay, but I'm going to slightly change the subject so that I can get back to them in a meaningful way in a moment. Okay. All right, so the problem with working with setoids is you personally impose a notion of equality. You define those EQ, blah, 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 blah. Maybe for one thing you define them wrong, you could, okay? But, okay, buyer beware, do whatever you like, okay? You can do that. But the issue that's happening here, what I'm trying to explain is, that type theory doesn't know that EQ is equality, okay? So you have to manually simulate equality, okay? You have to simulate the whole thing, and the whole thing is one big simulation, okay? It's terrible, okay? All right, so what I want to do now is broach the subject of equality, which is so difficult, okay? So what is equality? Well, it's going to be hard for me to give a precise and acceptable definition. But the best one that I know of is almost tautological. It sort of says, well, that which everything respects. You could say. Okay, this is not a definition, but it's a way of giving you some intuition. If you jazz it up, it can be called Leibniz's principle, but Leibniz's principle is just that. Things are equal if you can't tell them apart. That is, everything you could possibly do to them gives you equal results. You can't distinguish them. So this is Leibniz's principle. Leibniz's formulation is probably the best one that there is, even though it doesn't really pin anything down. Okay. So there's a way to express this inside of type theory through the notion of what is called the identification type. The reason to call it that is will become more apparent shortly, okay? But we'll call it the identification type. The reason I'm going to call it that is I want to emphasize, in the first few minutes of development I will suppress this, but I want to call attention to proof relevance. And so I'm going to call proofs of equalities, I'm going to call identifications, okay? So this will be the type of identification. So what is the identification type? It says, if you have A as a type, so we've decided that it was convenient to just say it inhabits a universe, and you have two elements of that type, you can speak of the type of identifications of M and N. It's also in U. Okay? So this is the identification type. So this is to be thought of as the type of identifications of M and N. There's another reason. So proof relevance is the main reason why I want to use that terminology. But the other reason is I'm going to point out is that we're going to stipulate that certain things be identified. We're going to introduce identifications to make them be the case. Make these certain equations be true, so to speak. So eventually what I'm going to get is a very grand generalization of the notion of quotient. Yeah. So I'm going to give a vast generalization of the idea of quotient. That's where I'm headed. Okay? All right? So that's what's going to happen. And as a matter of notation, and I know that this will be confusing, but it's unavoidable. As a matter of notation, This thing is sometimes written m equals a m. Okay? Now, here's the problem with it. The problem with that notation. You must remember, you have to turn yourself into a dyed-in-the-wool, die-hard, unrelenting constructivist. You have to understand that that's a type, so it has inhabitants. Okay? So this is a type. And it's the type of identifications of M and N in the type A. So the picture I'm starting to get to, I will amplify this as I go along, but the picture I'm starting to get to is one that looks like this. This is the starting point. We'll have this, which I'll think of as the type A. And there are a bunch of points in the type A, some of which are identified to be regarded as the same as one another. And these things are data, alpha, beta, gamma. Okay? Those are identifications. So those will emerge as elements of, if I called the endpoints here A and B, then alpha would be an element of the identification between A and B. That's the first starting point. There's much more to be said. Unfortunately, I will not come close to even saying what needs to be said. But, okay, so that's the idea of what the identification is. So you must remember, for this notion of equality, it is no longer the case that it expresses something that is at most true. That the reasons why it's true matter. Okay, that's what we're trying to get at. Okay? So it's not something that's at most true. So we're going to have to force ourselves to stop speaking about x equals y, except in restricted circumstances. We must speak about the way in which x and y are identified. Okay? So this is a way of dealing with certain issues that I will explain. Okay, so what are the introductions? So this is a formation rule. What is the introduction rule? Well, so this is fascinating. Let's do it. I have to leave myself substantial space, so let me be careful. Well, the introduction rule is easy to state. It says, if M is in A, then it is automatically self-identified. Which means I ought to draw, and now there's a big problem how to draw this. I ought to draw a little loop here, everywhere. Okay. Which represents reflexivity, the self-identification of, in this case, B with B. This is reflexivity of A with A, and so on. Now the problem with the notation is, I draw it small, but it's really a loop that doesn't go anywhere at all. It stays exactly at this point always. It doesn't really go out and come back, but there's no way to notate this. So the typical thing is you make a little loop and then where you mark it as reflexivity or something. You know, there's nothing you can do. Pictures have their limits. Okay, so this is the self-identification. Now there's immediately going to be an issue about what in the hell does reflexivity mean? Because you see, I've been talking to you all this lecture about the reflexivity or lack thereof of various types. Whether a function from n to n is equal to itself or n to n is equal to itself. Something is tricky about when I say reflexivity. When I write m equals m, am I not using some notion of equality to say that the two endpoints are the same, which is somehow different from equality? These things will make your head hurt, I can tell you. Okay. All right, so this is one introduction rule. This is the basic introduction rule. And now the big, complicated, always confusing elimination rule. Okay? Here's a way of justifying it, that if you peel it apart will raise more questions than it answers, but I bet it'll help you anyway. All right? Which is, if that's the only introduction rule, that's already I'm in a state of sin. But let me just say it as a way of being heuristic for you. If this is the only introduction rule, and by the way, it's not, but if this were the only introduction rule, then what I would be saying is the identification type is the least reflexive relation. See what I mean? That's all you need to know. Because if I want to map out of the identification type, I know that it's sufficient to map out of the instance of reflexivity. I'll explain all this, okay? Because if I can get it from reflexivity, then I can get it from anything in that type because it's the least reflexive relation. So I'll show you how this goes. So what I mean by this is the following. I want to show, given an identification, okay, so I need a whole bunch of premises. So I'm going to need that A is in U. Some of these can be taken as implied, but let me write it all out and hopefully not forget anything. We'll do this. And I want to say, I'm going to define it with a mapping out property, because if I'm going to think of it as the least such thing, the least reflexive relation, that the expression of the leastness is initiality. So I have a mapping out property. Okay? All right? Got it? So it's going to be a left adjoint. That will be the way of thinking about it in Ed's terminology. Okay? So we'll see. So it's on the left here. So the identity, so I want to map out from this. And what I want to do is get an element of C, and I'll emphasize C sub Z like I've done before. Where with, well, oh, sorry, that's not what I want to say. Pardon me. I want to say, give me one moment. Yeah, I want to say, let me do this in a slightly different way if you don't mind. I can do this in even more generality. Gives me something, and this will be in C, X, Y, Z. Okay, so I'm going to have X, A, Y, A, Z is the identification of X and Y. I want to know that C, X, Y, Z, just to emphasize, is in U. So if you want to think of it in terms of logic, I want to know that the property C holds of X and Y given that they are identified by Z. Okay? So you can think of this as like mapping out of a quotiented type. If I quotient the type, then I have to show that something is well defined. I want to say, well, give me two elements in such a way that they're identified by the quotient, and I want to show something. Okay, so this is what I'm going to do here. Okay, so I'm going to do this. So as I mentioned before, this thing is called the motive. Let's see. So you usually parameterize. So the lim form is called J, and it's parameterized by the motive. Okay, and it takes an argument. And then you apply it to Z, in this case it'll be Z, and we'll get some type like that. I hope that I'm doing this right. I decided on the spot to change my notation, so let's watch me get in trouble. Okay, I think I'm worried that I'm going to get into trouble. So let me move these up above the line. It won't hurt if I do it. And I might be able to do it that way also, but let's do it. So we'll get it. I'll fill this in a second. I'll do it with a substitution because I'm not sure I'm right. Okay. Probably I don't actually need to do the substitution. So this will be something correct. Okay. Let me make sure I'm right. Okay? The idea is that I have all this stuff, and moreover, I have an identification, alpha, between M and N. So if I just wrote this, you could take the other things to be implied, but anyway, I'm being suspended here. Okay, so I have an identification here, and I want to use that identification to show that, well, for M and alpha, let's see hold. Okay? That's the idea here. And the claim is that it's sufficient given X and A to give me a proof, let's call it little c, that C holds for X, X, and reflexivity. in which case this is written x dot m. Okay, and that's the elimination rule. So these premises are a little excess, so if you find it all very heavy, the main content is, I have a motive, I have an identification of M and N, and I want to show that the property holds of M, N, and alpha, where those are the data I'm dealing with. Alpha identifies M with N. So I want to speak about M, N, and alpha. And the idea is that it's sufficient, oh, sorry, that should have said C. Okay? The idea is that it's sufficient to show that this property, if you think of it as expressing a predicate, that this predicate holds for any self-loop. Okay, so that's the idea, given x and c. So another way of saying it all is, if this is a reflexive relation, and this is the least reflexive relation, then I can map out of this guy into C. You see? If this is if id AMN is characterized by this line, if that were the case, if the id A was completely characterized by this introduction rule, which means that, right, then that means that the identification in question, what I'm saying is that it's the least reflexive relation. That is, it holds between a thing and itself by virtue of this self loop. So if you give me any one, if this is representing the least reflexive relation, then it must be enough, okay, to map out of that to show that C is a reflexive relation, written like that, so that the least one can be mapped into it. This is the whole business about mapping out property. So I'm giving a mapping out property, okay, here. So the way I started to write it, I could also write it, now I'm confident because I have a moment of uncertainty. So I could also write this to make the mapping out more explicit. I would write it like I started to, and then I got cold feet. Okay? We can say J with that motive X, Y, Z, C. Z, yes, Z, okay, is of type C, X, Y, Z. If, and now you don't need this line anymore, and then you just need this premise and that premise. Okay? So that was the other way to do it. So I'm just saying, if C is a reflexive relation, then I can map out of it the least reflexive relation expresses that there's a mapping out property into C. So that's what this is on. So that's the elimination rule. Now it's going to take a long time to digest that. Oh, and I want to mention something about how to compute with it. What the calculation rule is, I have to put that somewhere. So let me put that here, so it's on the same board. If you take J with X, Y, Z, C, I don't care about that, and X dot little c, and you apply it to reflexivity at M, then that should be plug in M for X. The type, so I'm sorry, C, little c, M for X little c, whose type will be M Ruffle A of M and C. That should work out, yes. Because Ruffle A of M is a proof of id A M M. So I plug in M, M, and Ruffle. So M, M, and Ruffle is what I have here. And the code is this. Written right there. Okay, so that's the computational rule for that guy. All right, so let's look at a special case. So in order to digest this, let's look at a special case. One special case is something called transport. Okay, so if you don't mind, can I erase in place here? You don't want me to do that, all right? Okay, I'll write it over here. It has an important special case and an important consequence. We'll get to that in a second. The special case is something called transport. Okay. Let me just look at my actually prove this, okay? That's the idea. I'll write it off in post form. Suppose I have a family of types. Or you can think of it as a predicate. Okay, and I know that I have an identification in A, which is the index type, M and N. Then I want to say, there's two different ways to write this. Let me write it this way. Okay. And I want to say that there is a function called transport, or TR, which goes from x dot c is parameterized, and it takes alpha, and it gives me a mapping from M for xc to N for xc. That's the idea. So how are we supposed to picture that? Well, we have here A, and we have M, and we have N. C is a family of types indexed by A. So what we think of in balloon diagrams, we have here C, if you don't mind me writing, C of M. And we have here, okay, this is up here, in this balloon diagram, I have C of N. I'll give you the computation rule for transport in a minute, okay? But the idea is that if M and N are identified by alpha, then anything in here can be sent to something over here. That's the first basic consequence. It's a transport property that says if you give me something in this fiber, I will transport it over to something in this fiber. And that's the first thing, first basic principle. And it will satisfy the law that if the identification were reflexivity, then it's the identity function on C of M. Meaning that if I consider the self loop here, for reflexivity, then this guy is sure to be sent to itself by the transport property. It can't be sent anywhere else in this fiber. It's to be sent exactly to itself. That's what this is saying. So another way to write this rule is to put in an argument here. You say, give me, I don't know what, Q is in C of M, then this thing applied to Q will be in C of M. So that's the same general idea that I'm looking for, okay? So it's going to be a function that goes from here to here. So that's called the transport function. So the path lifts to the fibers in the sense that if I give an element of the fiber over M, I can take that element and shove it over here to the fiber over M. So what is this saying? Let me write it, let me undo this. It's nicer to see it this way. Think of it as a principle of logic. The fact is, because paths are, I haven't told you that yet. Well, this is part of the problem of teaching, is what order to say things in. You'll also be able to map it back. I'll have to explain that. There's a mapping in the other direction because this path can be reversed. I'll get to that in a second. Okay, so what I wanted to say was that this is like saying, if M and N are equal, and C holds of M, then it holds for M. And the part about going back is, and vice versa. In other words, these two sides are logically equivalent. Okay? That's natural property of equality. It's respected by predicates. Okay? Right? Should make sense. Equal things, if this holds, that holds. But as Frank pointed out to you, mere logical equivalence is a shabby notion. Okay? Saying that there's maps back and forth is saying very, very little. He gave you some crazy example, right? A arrow B cross C being logically equivalent to A arrow B arrow A arrow C. Right? I think he gave you that example. It's sort of showing you there's a logical equivalence. A logical equivalence is an extremely weak notion. It will turn out that this is actually equivalence. Okay? Which is a way of saying that there's a if these were to be thought of as sets, which they can't always be. But if every balloon consisted of a set of discrete elements, just discrete points, then it would say that they're in bijection. But they're not necessarily discrete points. They might be connected in certain ways. And then the notion of equivalence is a little more subtle because it must be well defined with respect to the notion of identification. But in the case of sets, so here's another idea that goes back to Cantor and Frege, is the conception of a set as sort of points devoid of any interpretation or substance, any context whatsoever. They're isolated points. The notion of a set and the notion of an arbitrary function go back to the 19th century, which is you're to think of a set as a collection of, well, I don't know what words to use. They're always going to be wrong. I'm tempted to say random, but I don't mean random. Okay? An arbitrary collection of things. Okay? And then when you talk about mappings between them, they're arbitrary associations. Okay? From one to the other. There's no requirement that any sort of structure be respected. They don't have to be homomorphisms with respect to any kind of algebraic structure. When I introduce identifications, a type of such identifications may no longer be a set. It's a little subtle to say. A lot of subtleties in this business. But it may not be a set. It may not be discrete anymore in a sense that I will explain. And then that tells you that equivalent, but then equivalence is something more complicated because I've got to show that the structure of identifications is respected, that identifications are mapped to identification. But if they're all self-loops, then that's trivial. You can always map the self-loop to the self-loop, and then you can recover the notion of an arbitrary function or a bijection between two sets. But when you have identifications going, you have to worry about the identifications, like you have to worry about respecting those. And what does it mean to respect them? It means that certain identifications have to be equal to certain other identifications. That's what's going to happen. So what's going to happen is we're going to have to start worrying about identifications between identifications. Okay? And that's a little bit what Ed was broaching this morning with two categories. I don't know if he used the word two category or not, but he told you about categories, functors, and natural transformations. The natural transformations are two cells. Okay? Those are, if it's a natural bijection, you can, between sets, let's say, like Hom sets, then it's an identification between two Hom functors, as an example of what he was giving you. That comes up with respect to adjoints. That's provided that the Homs are sets. But there's no particular reason the Homs have to be sets. They could, again, have further structure, okay, including structure of what's called a groupoid. And well, next time I'll start talking about that, and we'll see how that plays out. And that leads to the notion of an infinity category, which is a notion, or infinity groupoid, weak infinity groupoid, which is a notion that is captured by what I've started building here, this identification type. The notion of this infinite tower of identifications of identifications of identifications is neatly captured through the notion of identification type. And that's what has excited a lot of people. Because the infinite power of things that I'll explain next time is very, very hard to handle. But type theory is very easy to handle compared to that. And it turns out that there's a nice relationship between them, which is all to do with the identification type. And using the identification type, I will then revisit the issue of extensionality of functions, and I for sure will only be able to mention the concept of univalence, which is a further aggressive use of the notion of identification in the universe, where the A is the universe itself. Okay, and I will only be able to say one or two things about that. I won't have time. But I think it's more important for you to see the big picture than for me to work out technical details for you. So I'm going to try to walk that line so you can see what's going on. Because it's very hard to look at all the technical details and recover what the story is. So I prefer to tell you what the story is so that then you can read the technical details and you'll say, oh, that makes sense. Okay, so that's where I want to get to. Okay, so you'll have to do the actual sweat work yourself, but I hope to make it easier for you. Okay, so that's the plan. So let's finish up for that. All right, questions? I'm very happy to answer questions.
reflexive, what do you mean by that?
Well, when I say what, sorry?
Least reflexive?
Well, it's sort of like when I said, starting in the very beginning, I talked about the join being the least amongst the upper bounds. So it has a mapping out property. The join tends to be less than or equal to things. If x is less than or equal to z and y is less than or equal to z, then the join is less than or equal to z. So it tends to be less than or equal to things. It has a mapping out property. Okay? So if I think of the introduction rule as an inductive definition that says the only thing that goes into the identification type is reflexivity, the situation is in fact more subtle than this, but let me just say it, okay? If the only thing I put in it is reflexivity, then if I take any other relation that has the property of being reflexive, if this is the one that contains only that, then it's going to be contained in C. That is, I can map from this guy into C because it's, so to say, less than or equal to it. When I went from preorders to categories, I said, take a preorder with evidence. So being the least amongst things turns into a mapping out property, that there's a map from the thing to everything else in that class. So there's a map from the join to everything in the class of upper bounds of x and y. Right? You see, that's your mapping out property. If I look at all the things that are upper bounds of x and y, the join of x and y is less than or equal to them. It means there's a map out of the join to any particular upper bound you can name. Okay, right? So here you have the same general characteristic. Amongst relations that are reflexive, this is the least reflexive one, so it maps out of it into that relation. Okay, that's the idea. Now I will explain where I'm tricking you. When I say that something contains only reflexivity, there's a hidden use of equality in there. I'm saying everything that's in there is reflexivity. What does is mean? I told you in the very beginning, the whole burden of my lectures is to make clear the subtleties of equality. So I really used equality. So what's going to be interesting is I'm going to put in lots of elements in the identification type, all of which will be is reflexivity. That's kind of shocking. And here's the way it works. I'll just give you a flavor. So when I say that everything in here is reflexivity, what I mean is that, okay, go back to this picture. In general, what I mean is, let's see if I can think of what's the right way to depict it. What I mean is, I have reflexivity. Let me just write it here. So I have some endpoint, M. I'll write M twice. It's easier. Rather than write it as a loop, it'll be hard. What I'm going to end up meaning is that there's a cell. If I have, well, what's going to happen is, I have M and N. And I have an identification here, and I have an identification here, and I have an identification here. You can look at it like that, ruffle of M. This square exists, that there is such a cell. So what it's saying is that I can deform any path into reflexivity along the identifications on the left and the right endpoints here. So if I smush these two things down, I'm saying alpha goes to ruffle. So the idea about is so what's happening is that this is to be thought of as a point in the identity type. This is to be thought of as a point in the identity type. And this cell is to be thought as a line or an identification between them. That's essentially what's going to happen. So the notion of is, I'll explain that more carefully next time. The notion of is up to a higher cell. So the picture that we're going to get going looks like this. I'll erase that. I'll make it all more precise next time. I start out with points of various kinds, and I have identifications between them, like willy-nilly, who knows where they are. I have the idea that I can have two parallel identifications, alpha and beta, and then I can speak about whether those things are equal to each other or not, which will be an identification between these identifications, sometimes written as a double line. But I can also have multiple identifications between alpha and beta, call those delta and gamma. And then those things can be identified by some eta or something, or epsilon, written here, and so on to infinity. Okay? So my notion of one way of thinking about this is that, if I speak loosely for the sake of entertainment, if I think of an identification as a lie, the lie will be true, will be valid up to higher lies. Okay? That's what's going to happen. So an example of what's going to happen, for example, is we will be able to talk about alpha followed by alpha inverse, which I can concatenate. These will have the same endpoints, m and m. I can make that alpha dot alpha prime. I also have the reflexivity, and one of the laws will say that there's a cell that relates this composition to reflexivity. So there's a higher identification that says that the identification of m and m given by alpha followed by alpha prime is identified with the reflexive self-loop of m. Okay? That's what's going to happen. And so that's an example of what is called the groupoid law. So the point is, that's a particular groupoid law. I want to say approximately alpha dot alpha prime equals, what do I mean by equals? The identity. But what do I mean by equals? Well, what I mean is, it's identified with. There's an identification. In the identifications, amongst the identifications of m and m, there's an identification between these two identifications. That's another way of saying it. Okay? So that kind of picture can be written like that. The type that we're talking about identifications in is the identification type of m and m. This is an identification of m and m. This is an identification of m and m, and I'm going to identify those. There will be something in here. Okay? So that will be required. But that something itself is an identification, and it itself can be concatenated with another identification, maybe its own inverse, which means there has to be yet another higher identification of those two identifications, and they have to exist all the way up. So the picture is that a type is going to be infinite dimensional. So what we start out with at dimension 0, we have the points, or the elements of the type. At dimension 1, we have the lines, which are identifications of points. And then at the next dimension, we have identifications of lines, which are sort of disks or something, of parallel lines in the way I'm drawing it now. If I have two parallel lines, I can identify them, so that's sort of a disk. And I can then go up in dimension 3, and it'll be a solid sphere. Right? Because I'll take two of these disks that can be identified because they have the same boundary, and glue them together and fill in the interior, and I'll get a sphere. Okay? So we'll get spheres, and we'll go on like that. Okay? And that's the kind of structure that you get. Yes?
So just with the identification type that you spoke about today, would you get any of that higher structure between the identification types?
What we learned today, do we get any of that yet?
What's that again?
Do we get that from what?
What we've done today.
results of-
Yeah, I've already got enough on the table to talk about all that. That's all present. Okay, I haven't yet shown it to you, but I will. Okay, so that's the plan. So this is already, this structure is present. Because it's all, in this setting, it's all in the iterated identity type. Okay? Because I can talk about identifications between points in A. Then I can talk about, and those are lines. And then I can talk about identifications of lines. There's a line, I identify that line, so it's a disk. Because there are lines that have to have the same boundary, the same endpoint. Okay? So this picture is the picture of what is called a globular set. And a particular globular set that satisfies a certain sufficiency condition is called an infinity groupoid. That's the structure we will actually have. There's another way to talk about the same structure using squares and cubes and so on. And there's another way to talk about it using triangles and tetrahedra and so on. There are different combinatorial objects that can be used to explain the same general picture. But the one that's very natural with type theory is the globular approach, where we have things with common endpoint are identified, and then their boundary, if I have two things with the same boundary, I can identify them, which is filling in the interior, and that's how I get these end spheres. So everything is a globe or an end sphere. Yep.
Is it true that when you write down the introduction rule, you're sort of forced to have these higher identification types?
So again.
So the introduction rule you wrote for the identification type,
Yep.
are you forced to have higher ones once you write it down?
Yes, in essence, yes. They're already present. I mean,
Right.
because the identification type is a type,
Right.
and there's an identification type for every type. So I cannot avoid the fact that there's an identification type of identifications of identifications of identifications. So that structure is present. What's interesting is that it has the structure of the infinity groupoid,
Okay.
which is related to the, which basically is saying that there are enough cells.
So you don't have to impose the groupoid law.
What's that?
You don't have to impose the groupoid law.
No, the groupoid laws are already present. That's what's remarkable, okay? I haven't shown that yet, but the groupoid laws are already present. And so I'll show you how to derive the groupoid laws, okay, for yourself. Well, the point is that we've done away with the notion of an equation being just true simplicity. That's the point you've got to get into your head. So when I say, for example, that the concatenation of these identifications is associative, that's a little bit of an abusive notation. What I really mean is there is an associator, which is a proof that the associative law holds. There's an identification of two associations of a three-step composition, okay? So you have to break yourself of talking about, oh, this is equal to that. So in ordinary algebra, like groups, you have x times x inverse is equal to e, the unit element, etc. Okay? Here, we're working with higher dimensional structures where equality doesn't mean something that just is the case. Okay? I talk about the reason why they're equal, okay, which is the identification. But now, when I've done that, I've introduced another object in the discussion, namely the identification itself. And then those identifications can be multiplied, and then they have to satisfy an associativity law, which means another identification must exist. So what's happening is you have this infinite dimensional structure such that there's a sufficiency condition, that there have to be enough cells. It has to be sufficiently well populated, okay, so that all of the laws that you demand are witnessed by identifications in that hierarchy. And if you have sufficiently many identifications, then you have a structure in which to interpret type theory. Okay, that's enough to interpret type theory. If you do this with simplices like triangles to all dimensions, or if you do this with squares or cubes to all dimensions, okay, then you are dealing with an object called a simplicial or cubical Can complex. And the notion of being a Can complex just means that there's enough cells, there are enough cubes laying around to witness all of the things that have to be the case. Okay? And I won't have time to explain this, but there's a very, very remarkable way, I still find, years after learning it, there's a very remarkable way to say in one line practically, when you have enough cells. Okay, so we'll get, probably won't have time to talk about that. Okay, but the so-called Can condition is the thing that concisely summarizes the sufficiency when you have enough. So, okay, so that's the picture we're going to develop next time. And the problem that remains open is to give a computational meaning to all of this. Okay? How do you compute with these things? And I don't know if I will have much time to discuss that. There's lots of effort going on that problem. And it has proved to be quite challenging. Okay, other questions? All right, okay, enough for today.